S3, S4 physics, electric fields. Electric fields. Potential difference, voltage definition. A measure of the energy given to the charge carriers in the circuit, normally from the supply. We can see here an example of an electric field. The balloon is statically charged. There's a potential difference between the cat and the balloon, and so the hairs are standing on end because of the electric field. An electric field exerts a force on a charge. We can also see this in the classroom with the Van de Graaff generator. Charges come in two forms, positive and negative. Like charges, that is, charges that are the same, for example, positive and positive or negative and negative, repel each other. Opposite charges attract each other, hence the phrase opposites attract, similar to the north and south poles of a magnet. We see here the positive and negative charges, and around these charges there are electric fields. These can be shown with field lines. All charged particles experience a force when they are within an electric field. That force will make the charged particles move in a predictable way. That is, we can predict the path of a charge within an electric field given the direction of the electric field and the charge on the particle. And this is a National 5 outcome. Even a single point charge, positive or negative, will have an electric field around it, and it's that electric field that decides how another particle is going to interact with it. Field lines going out of a positive charge and the field lines go into a negative charge. We can see that the field lines are equally spaced around the charges, and they're heading out in all directions from the positive charge and heading in from all directions of the negative charge. When drawing field lines, we need to follow some rules. The field lines must be evenly spaced around the point charge. The lines must be drawn with a ruler. The arrows on the lines show the direction in which the positive charge would move within a field. So for example, if a positive charge came close to a positive charge, it would be repelled. That's because positive charge has field lines going out the way, and the arrows represent the direction a positive charge would act when interacting. Positives repel each other, so the positive charge would move away. Whereas if this was a negative charge, and we draw the field lines, a positive charge coming towards this is going to be attracted. So the field lines go in to the negative charge. Examples of more complex fields are shown on the next few slides. Here we can see the field lines which exist between a positive and negative charge. So the positive charge has field lines going out the way, going towards the negative charge, which has field lines going in. We can see within this we have a central straight line in between them, but then the field lines become curved and further apart. The spacing in between the field lines give an indication of the strength of the electric field. At the ends of the charges, here and here, we can see that the field lines are very close to each other. So here the electric field is at its strongest point. There is a force of attraction between the positive and negative charges because the field lines are going into each other. Here again, we see a simplified version, and this is what you'd be expected to draw within a National 5 assessment, showing several field lines coming out of the positive charge, going into the negative charge, and the field lines in between. And also we can see with a positive and positive charge that there is this space in between. That shows the repulsive force between the charges. Again, positive charges, the arrows are going out. However, we could draw the same diagram with negative charges and the arrows would be reversed. Within a uniform electric field, we have a positively charged metal plate and a negatively charged metal plate. And this metal plate may be opposite ends of a conductor. Field lines are drawn between the positive and the negative, going in the direction as we'd expect, and a particle is placed within the field. The direction of that particle is going to depend on whether that particle is positively charged or negatively charged. If this particle was negatively charged, it would go against the field and go towards the positive plate. If this particle was positively charged, it's going to go with the field and go towards the negative. If we show a simplified diagram of this, here we have a positive and negative terminal. Between those is an electric field. A positively charged particle will be attracted towards the negative and repelled from the positive, following a curved path like a projectile through the electric field. A negatively charged particle is going to act in the opposite way. It's going to be repelled by the negative terminal and attracted by the positive terminal. Again, following a curved path, but this time curving upwards. If a particle enters the field and it has no charge, then it simply passes straight through. Though it should be noted that eventually it would curve slightly, but that's due to gravity, not because of an electric field. So have a look at this diagram. Could you complete to show the path of the electron through the electric field? Now remember, the electron is negatively charged. So because it's negatively charged, it's going to be repelled from the negative side and attracted to the positive side. So if we continue the path of the electron, go straight through, and then is going to curve up and towards the positive terminal. Another example of this is shown in the next slide. This is a past paper question. A uniform electric field exists between plates Q and R. The diagram shows the path taken by a particle as it passes through the field. Which row in the table identifies the charge on the particle, the charge on plate Q, and the charge on plate R? So let's have a think. We can see that the particle is being repelled from R and attracted towards Q. That tells us that R has the same charge as the particle and Q has the opposite charge of the particle. So let's look at our options. Option A, saying the charge on the particle is negative, the charge on plate Q is positive, and the charge on plate R is negative also. This makes sense. Negative particle going in is going to be attracted towards Q because we're saying Q must have the opposite charge of the particle, and it's going to be repelled by plate R because we're saying R has the same charge as the particle. So that's our correct answer. Let's check the other ones just to check. Negative particle going in. If Q is negatively charged, we would not see that path. We would see the particle being repelled from plate Q. So that's definitely wrong. If there was no charge on the particle would continue straight through the field. So these two are both wrong. If there was a positive particle going in, again, it would be repelled from plate Q if it had the same charge. So that one's wrong. So our answer is definitely A.